In this topic, we will discuss about the problems which appear from the section of particle in a box in different exams like NET and GET exam. The first question here reads like this: the degeneracy of the state having the energy 27 h square by 8 ml square for a particle in a 3D cubic box of length L is. We need to find the degeneracy of this energy state. For this, we have a formula. From the formula, we can find the energy expression. So, the energy of a 3D particle in a 3D cubic box is given by En is equal to nx square plus ny square plus nz square h square by 8 ml square. This is the energy of a particle in a 3D box. Now, the energy given is this 27 h square by 8 ml square. When comparing these two, we will make this nx square plus ny square plus nz square is equal to 27. So this nx square plus ny square plus nz square is equal to 27. Further, we need to find the set of quantum numbers. When they are squared and added, we will give 27. So those are, if we assign 5 to nx and 1 to ni and 1 to nz, then square it, you will get 27, 5, 1, 1. And the same quantum numbers can be arranged in this way. Nx is given, ny is given 5, and nz is given 5, then 1, 1, 5. The other set of quantum numbers which would give the same energy is only having the quantum number 3. Nx is equal to 3, ny is equal to 3, and nz is equal to 3. Then it would make 27. So these are the four sets of quantum numbers given to nx, ny, nz that would correspond to this energy. So the degeneracy of this energy level is 4. Next question, which appeared in GATE 2010, an electron of mass m is confined to one-dimensional box of length b. If it makes a radiative transition from second excited state to the ground state, the frequency of the photon emitted is. So this is a 1D box. This is a 1D box, and here are the energy levels, and this is the ground state energy level, and this is first excited state energy level, and this is second excited state energy level. Now it is making the transition from second excited state to the ground state. So this is the second excited state. It is making from a second excited state to the ground state. As we are in a particle in a one-dimensional box, this is the energy equation for a particle in a 1D box, and this is the energy expression for a particle in 2D box. And as we have seen earlier, the energy expression for a 3D box, a particle in a 3D box, we will use this equation. But for this problem, we need to have only the energy expression for a particle in a 1D box. Nx is equal to nx square h square by 8 ml square. Now we need to find the energy of the second excited state. This is the second excited state, and this is the ground state. Second excited state, we will, if this is assigned, the n is equal to 1 for a 1D box, the particle will the particle in on a 1D box, the quantum numbers that would take is 1, 2, 3. These are the quantum numbers given for a 2D box, and these are for a particle in a 3D box. And for this level, this E3 and this is E1. Now we need to find the E1 and E3, then take the difference between them, then we will find the answer. So for a 1D box, use this equation, and we will need to find the E1 is the ground state. E1 is the ground state. The energy it gives when you substitute the value of n here is h square by 8mb square. And here b is the length of the box. Here L is made B. The second excited state is n is equal to 3. When you substitute 3 here, you will get 9h square by 8mb square. To make the radiative transition from here to here, we take the difference in energies between E3 and E1. That would give you 9h square by 8mb square minus h square by 8mb square. When you take this common out, then you will be left with 9 minus 8, that is equal to 8h square by 8mb square. This h 8 and 8 gets cancelled. Then this difference can be made equal to h nu. So we need nu here, the frequency corresponding to that transition. Then h would go to the denominator here, then one h here and one more h there would get cancelled, and finally we are left with the h by mp square. This is the frequency corresponds to the transition from second excited state to the ground state. So this is the option. Now here is one more problem which was asked in say SIR June 2019 exam. For a particle of mass m in one-dimensional box of length 2l, the energy level corresponding to n is equal to 4. So we are now in a particle have a particle of mass m in 1D box. So energy expression for 1D box is taken here. En is equal to n square h square by 8ml square. The only change we should make it here, the length of the box is, this is general expression of a box of length L, and in this case the length is 2L. So to substitute L by 2L, then you will get 4L square. Then you will get, instead of L square, you will get 4L square. That 4 into this 8 makes 32 ml square, n square h square by 32 ml square is the energy expression for this 2L length, for the length of the box of 2L. Then from this energy expression, then we will get the, when you substitute n is equal to 8, we will get the energy corresponding to, energy corresponds to n is equal to 8 state. You substitute 8, you get 64 here, then in the denominator we have 32, then it becomes simplified to E8 is equal to h square by m l square is your answer. And this is a problem which was asked in CSR December 2017 exam. The correct statement about the difference of second and first excited state energies of a particle in 1D box, 2D square, and 3D cubic boxes with the same length for each. We have the same length for each box. First, we need to find the energy difference between the first excited state and the second excited. This is the first, this is the ground state. E1 corresponds to ground state, and E2 is the first excited state, and this is the second excited state. What is asked here, what is the difference between E2 and E3 in 1D? What is the difference between E2 and E3 in 2D box, and what is same in 3D box? So for that, we need to take the different energy expression correspond to 1D box, 2D box, and 3D box. So this is for 1D box, a particle in a 1D box, and the expression is Nx is equal to Nx square, h square by 8ml square, and this is for 2D box, Nx square plus Ny square, h square by 8ml square. We need to find the energy difference between E2 and E3, as these are the two corresponds to the second and first excited states. So this is the first excited state, and this is second excited state, and this is ground state. So we need to find the energies corresponds to E2 and E3 in case of a 1D box. So E2 gives 4h square by 8ml square. E3 gives, substitute 3 here, it will become 9h square by 8ml square. And the difference between these two is delta E is equal to 5h square by 8ml square. This is the difference between the first excited and second excited state of a particle in a 1D box. Now we should calculate the same thing in the 2D box. In the 2D box, the second excited state, this is the second excited state, the quantum numbers, this Nx and Ny takes are 1, 2, or 2, 1, both it can take, and the quantum numbers the second excited state will have is 2, 2, and the first excited state, this is the first excited state described by the quantum numbers 1 and 2. When you substitute the 1 and 2 here, you will get 5h square by 8ml square. And for the second excited state, which will be having the quantum numbers 2 and 2, you substitute those two here, you will get the energy corresponding to second excited state in the 2D box. So if you take the difference, you will get delta E is equal to 3h square by 8ml square. Now same thing is done with respect to the 3D. We need to find the energy difference between E2 and E3. E2 here is the first excited state. E3 is the second excited state. The first excited state is described by the quantum numbers 1, 2, 1, or it can be 1, 1, 2, or it can be 1, 1, 2. Any one side you can take and calculate the energy here. And for the second excited state, you can take the quantum numbers 2, 2, 1, or 2, 1, 2, or 2, 1, 1. Any one side, all the three sets of quantum numbers which describes the second excited state will give the same energy as 9h square by 8ml square. When you take the difference between these two, you will get 3h square by a double square. So if you compare the energy difference of E2 and E3 in case of 1D, 2D and 3D, in case of 2D and 3D, the energy difference between the second excited state and the first excited state are equal to 3h square by ml square. But the energy difference between the second excited state and first excited state in case of 1D box was 5h square by a double square. So this energy difference in case of 1D box between E2 and E3 is greater than the same with the 2D and the 3D, both are equal. So the action which is correct is this one. The energy difference in 1D box is greater than delta E of 2D and delta E of 3D. This delta E is E2 minus E3 or E3 minus E2. See, 5h square by a table square. In case of 1D, the difference in energy. In case of 3D and 2D, this is 3h square by a table square. So these two are equal. These two are equal, but this is more than this. Go to the next problem. This is the question which was asked in again gate 2011. The wave function for a quantum mechanical particle in a one-dimensional box of length a is given by psi is equal to a sine by x by a. We need to find the value of a for a box of length 200 nanometer. Now the wave function is given. Now we are asked to find the normalization constant, where a is called the normalization constant. For finding the normalization constant, we use this relation. This relation is integration of 0 to a, integration of 0 to a, psi star psi dx is equal to 1. This psi star is the complex conjugate of the given wave function. This psi is the given wave function, and these are the limits from the box length 0 to box length a. And psi star is just the complex conjugate of given wave function, as it doesn't contain any complex numbers. So the psi star is same as psi. So psi star is same as psi a sine pi x, a sine pi x. Psi star is a sine pi x, then psi also is a sine pi x dx. Now we should find this integral, the value of this integral, and make it equal to 0. Then from that we will get the value of a. First we should find the value of this integral. Then if you integration of 0 to a into a square, and sine pi x into sine pi x is sine square pi x dx. Then from this, if you need to make use of this formula, sine square theta is equal to 1 minus cos 2 theta by 2. As we have sine square pi x by a, then the sine square pi x by a according to this relation can be written as 1 minus cos 2 pi x by 2. That 2 is written here, and a square is taken outside of the integration as it is a constant. It is taken outside of the integration, and this 2 which will be coming here down is written here. So we are now left with 1 minus sine square theta is equal to 1 minus cos 2 theta. Everything by x by a is taken as theta, 1 minus cos 2 theta dx. Then we should integrate separately this term and this term, a square by 2 integration of dx minus a square by 2 integration of cos 2 pi x a dx. So when you integrate this one, a square by 2 is written as such, then integrate dx, we will get x, and the limits are 0 to a minus a square by 2, and now we are integrating the cos 2 pi x by a dx. Integration of cos 2 pi x is sine 2 pi x a by 2 pi by a, then it is taken to the numerator, it will become a by 2 pi between the limits 0 to a. When you substitute the values of the integration limits for x, it will become the upper limit is a instead of x, the upper limit is a minus lower limit is 0, then minus it will become a 0, a square by 2. Then if you substitute the upper limit and lower limit in sine 2 pi x by a, x takes value a ones and 0 ones, and this gets cancelled. We are here left with sine 2 pi. The value of sine 2 pi is 0, and here it is sine 0. 0 minus 0 is 0. 0 into this would become 0. Here we are left with a square by 2 into a. So now we got the value of the integral is a square by 2 into a. This value of the integral is made equal to 1. From this expression, you can find this capital A square is equal to 2 by A. This A, small a, is the length of the box, that is given as 200 nanometer. Then we will substitute the value of, then from this, value of capital A is equal to square root of this. So it is written individually, root 2 by root A. Root A is 200 nanometer. Then that is, when simplified, you will get 0.1 nanometer power minus 1 by 2 is the answer for this question. And here is one more question which was asked in CSR December 2018 exam. It is about finding the average value of the position of a particle in the states corresponding to the quantum number n is equal to 1 and n is equal to 2. And we need to find the position of the particle. We need to find the position of the particle in the wave functions given by psi1 root 2 by L. This is general equation for the wave function. The general wave function equation in case of particle box is root 2 by L sine n pi x by L. If this n is 1 and make n is equal to 2, you will get psi 2. Psi 2 is equal to root 2 by L sine 2 pi x. You just write 2 here, it will become psi 2. If you write 3 here, it will become sine 3x. If you write 4 here, it will become psi 4. Like that, you need to find the value, substitute the value of n here, so as to get the wave functions correspond to different states. So psi 1 now is written as root 2 by L sine 1 pi x is same as sine pi x by L. So this is the equation we will use to calculate the average value of position, or for that matter, average value of any observable is calculated by using this equation. In this case, we need to find the average value of x is equal to integration of 0 to L psi 1 star x. This x is the same as this psi 1 star x psi 1 dx by integration of 0 to L psi 1 star times psi 1 dx. The value of this would will become equal to 1 because we have taken the normalized wave function. We have taken the normalized wave function. As we have taken normalized wave function, the psi star psi dx is equal to 1. So this term will make it to 1 and will not be carried further. So this is equal to integration of 0 to L psi 1 star, as it doesn't involve any of the conjugate complex numbers. This psi 1 star is same as psi 1 root 2 by L sin pi x by L x into psi 1 is this one, same root 2 by L sin pi x by L. Then root 2 by L into root 2 by L will become 2 by L, that is taken outside. Then sin pi x into sin pi x is sin square pi x by L into x. This x is written here, dx. You just make it dx is equal to, then using the formula earlier, 2 sine square, you just take this inside of this, 2 sine square theta can be written as 1 minus cos 2 theta. Just take this 2 inside of the integration, then you can read like this, 2 sine square theta, that 2 sine square theta can be written as 1 minus cos 2 theta, where theta is equal to pi x by L. Instead of sine square pi 2 sine square pi x by L, you can write this. Then this x is written here dx. Then you multiply this x with this term once and this x with this term once. Then do the integration separately, and for that we need to make use of this integration of product of two function. Integration of the product of two functions can be done by integration of u v dx is equal to u into integration of v dx minus integration of v dx du dx. Now make use of this formula to the integration for this term. This term after multiplying will become x cos 2 pi x by L. When you do that according to that formula, then you will get this one. Then when you apply the integration limits, this will become 0, as it is sine 2 pi. When you substitute x, the value of x by L, then L and L against sine 2 pi is 0, minus when you substitute the lower limit, then also it becomes 0. And this part will be cos 2 pi x by L will be, after substituting the upper limit and lower limit, will be 1 minus 1. That also would become 0. So whole part, everything this would become 0. Now only thing we are left with, so it was the integration of x dx will become x square by 2. Then you will end up getting the average value of the position in the state n is equal to 1, or psi 1 is L by 2. Now do the same thing, finding the average value of position of the particle in the wave function corresponds to n is equal to 2. Then this is the wave function corresponds to n is equal to 2. So root 2 by a sine 2 pi x will take and do the same thing what is done earlier. Then this sine square theta formula is used. In this case, sine square theta is 2 pi x by L. So cos 2 theta will become 4 pi x by L and multiply and do the integration separately. And this whole term will become 0, and what is that we are left with only this term. This term is 1 by L into integration of root 0 to L x dx is x square by 2. You substitute the limit, upper limit and lower limit for the value of x, then you will get L by 2. So the average value for the state for the wave function with n is equal to 1, and for the other wave function with n is equal to 2, for both the wave functions psi 1 and psi 2, the average value is the same as L by 2 and L by 2. Now we are asked to find the difference in the average values of the particle in the state described by the quantum number n is equal to 1 and the other state described by the quantum number 2. In both cases it is L by 2. You take the difference, you will get 0 is the answer. And you must remember here is this average position is independent of the quantum number. This is a problem which was also asked, which is also very important from the examination point of view. So this is little difficult. Consider a one-dimensional infinite square well. V of x is equal to 0. This is the in this range of the box. The potential is 0 and infinity otherwise. If a perturbation is applied of a perturbation delta V is V naught for 0 less than x less than a by 3 and it is 0 otherwise is applied. Then the correction to the energy of the first excited state. The correction to the energy of the first excited state to the first order. First excited state to the first order. Now we need to do the correction to the first excited state. For first excited state, the n value is 2. For the first excited state, n value is 2. So we need to take psi 2. We need to take psi 2 here. Psi 2 is root 2 by a sine 2 pi x by. So this is the first order correction on E2. For E2, then the wave function corresponding to psi 2 star delta H, this is the perturbation potential, first order correction to the energy of the nth state. So this symbol reads like this, is a first order correction to the energy of the nth state. So psi star n, so this is given in Brand-Ket form that can be taken to the integration form like this. So psi star, the perturbation potential, psi divided by psi star psi, as this value will become equal to 0 because we have taken the wave function which is normalized. So when it is taken to the integration form, the first order correction to the first excited state is E2 here is equal to root 2 by a sine 2 pi x. Now this is now taken to integration form. Just there is no 2 by here. Integration of 0 to a by 3 because we are doing the perturbation is in the length range of 0 to a by 3. So integration of 0 to a by 3, then psi 2 star root 2 by a sine 2 pi x by a V naught. V naught is the perturbation potential in this length range, and psi 2 is root 2 by a sine 2 pi x by a dx. Then this root 2 by a, this root 2 by a will come outside of the integration, will become 2 by a, and this V naught also is a constant. It will also come outside of the integration, will become V naught. Then so there is no this term 2 by a. This has to be 1 here, and integration of 0 to a by 3 sine square 2 pi x by a dx. Then if you take this 2 outside into the integration, it will become 2 sine square theta. That by the equation earlier relation, 2 sine square theta, 2 sine square theta is equal to 1 minus cos 2 theta. Then you do the integration separately. V naught by a into dx minus V naught by a cos 4 pi x by a. Then you just assume here, you simplify, you will get the answer as V naught by 3 plus 0.06 V naught is equal to 0.39 V naught, which is close to this answer. And here is one more important question about length of the particle in a box system. The ratio of the energy of first excited state E1 to that of the ground state of a particle in a three-dimensional regular box of sides L, L, and L by 2. This is a, now we have a particle in 3D box whose lengths are not same in all the three directions. The length of the box in x direction, if you take L, and in y direction also it is L, but in z direction it is L by 2. So this is the equation we know for the energy of a particle in a 3D box. The ground state energy E is equal to nx square plus ny square plus nz square h square by 8 ml square. Now when you write the same equation in this form, you just divide this L square individually to nx square, ny square, nz square. Then we are now left with for the ground state, E naught, the ground state E naught in a three-dimensional box is represented by the quantum numbers nx is equal to 1, ny is equal to 1, and z is equal to 1. Then we will write this to be initially don't take this 3, we will just individually divide this L square to all the 3. So nx square by L square plus ny square by L square plus nz square by L square. But along the z direction, the length of the box is L by 2. So this would become equal to, instead of L square, it would become L square by L by 2 whole square. L by 2 whole square, as it becomes equal to L by 2 whole square. Then this would 4 go to the numerator. So this gets modified to nx square plus ny square plus 4 nz square. There is no 3 here. There is no 3 here. Don't consider this 3 and this 3. We're just modifying this equation by individually dividing L square to nx square and ny square, nz square, and substituting the value of L in the z direction as L by 2. Then it will become L by 2 whole square. L by 2 whole square is L square by 4. This 4 would go to numerator. That's what it gets simplified to this form without this 3. So now the ground state E naught is described by the 3 quantum numbers 1, 1, 1. Substitute the values of here 1 square plus 1 square plus 4 into 1 square, that will become 6h square by 8 ml square. And for this same box, now the energy expression is this without the 3, then for the E1 state is described with the quantum numbers 112, R121, R21. You can take any one set that would correspond to the energy of the E1 state. The first excited state is E1. Then you substitute 1 to 1 here, 1 square plus 1 square plus. So these are the quantum numbers. In case of this is not a regular a cubic box, as it is not a cubic box, the quantum numbers 112, 121, and 211 would yield different energies. When I calculate, when you take this 112, the value of this will become 8h square by 8 ml square, because 1 square plus 1 square plus 4 into 4, 4 into 4, that will become 18. Or when you take this 1 to 1, is 1 square plus 2 square is 4, 5 plus 4 into 1 square, 9. So this set of quantum numbers will give higher energies, but this set and this set of quantum numbers will give a lower energy. So that would become the energy of E1. So we will assign nx is equal to 1, ny is equal to 2, and nz is equal to 1. Then it will become 1 square plus 1 square plus 4 into 1 square. 1 square plus 2 is given to this y. plus 4, 5 plus 4, 9h square. So E1 is now 9h square. E1 is now 9h square by 8ml square. We don't use this set of quantum numbers, and this set of quantum numbers will give higher energy than these two. Then we will go to the energy which is less when we give this set of quantum numbers. Now we need to find the ratio of E1 to E0. E1 by E0 is equal to 9h square by 8ml square into 8ml square by 6h square is the energy of the ground state described by these quantum numbers. So that would become equal to 9 by 6. So this is in the ratio 3:2. And this one more question. A quantum particle is subject to the potential V is equal to infinity in this range and V is equal to 0 when minus a by 2 less than x less than a by 2. The ground state wave function of the particle is proportional to. When the length of the box is like that, minus a by 2, a by 2, each wave function can become odd or even. Or we can classify according to the symmetry. As it is symmetrical, this will be taken as along x and negative, along minus x and plus x direction. It is symmetric, so it's taken as even function. The even functions will be having the wave function psi n is equal to root 2 by a cos n pi x by a, where n takes all odd values. And for the wave function which is odd, the function which is odd will be described by the equation psi n is equal to root 2 by a sin n pi x by l, n by x by a, if a is the length of the box, is equal to n is equal to 2, 4, 6. Now the ground state wave function of a particle, is symmetric. If it is symmetric, this is the ground state wave function looks like this. If it is symmetric, it will follow this equation. If it is not symmetric, if you just imagine a reflection symmetry here and this part and this part, then it will not be symmetric. So we will take the wave function like this. Psi n is equal to root 2 by a sin n pi x by a, where n is all even. So from this, the ground state wave function for a particle in a box of length like this, minus a by 2, a by 2. If it is symmetric, the ground state is symmetric, a cos function will be the wave function and cos pi x by a. Here n is equal to 1. The ground state n takes the 1. The ground state wave function of a particle is proportional to cos 1 pi x by a. In this problem, a two-dimensional square rigid box of side L contains 6 non-interacting electrons at t is equal to 0. The mass of the electron is m. The ground state energy of the system of electrons in units of pi square h bar square by 2 ml square is. So we need to find the ground state energy of the electrons. As we have 6 electrons, and as we know, the spin of the electron is half. The spin multiplicity must be 2, 2s plus 1, 2. So we can arrange in every energy level 2 electrons each we can arrange. As the spin multiplicity becomes equal to 2, these many number of electrons can be arranged in each energy levels. As we have 6 electrons, 2 electrons can be arranged in the ground state, and 2 can be in first excited state, and 2 can be in second excited state. So we need to find the energies corresponding to all the 6 electrons. 2 electrons are present in this state, so the energy of them is 2e1, plus 2 electrons are present in e2, so their energy will be 2e2, and 2 are in e3. So the total energy will be sum of all the energies of the electrons, 2e1 plus 2e2 plus 2e3. As we are present in two-dimensional bags. For the two-dimensional bags, the quantum numbers which would make the E1 system is E11. E11. So the formula we will use for the two-dimensional box is E nx ny is equal to nx square plus ny square h square by 8ml square. So nx square plus ny square value will become 2 h square by 8 ml square. So the energy of this level for a 2D box is E either 1 2 or 2 1, then will become 5 h square by 8 ml square. The energy of this state is described by the quantum numbers E22. E22, then that would be 2 square plus 2 square makes it 8 h square by 8 ml square. So we have 2 electrons in A1, 2 into E1, it will become 4 h square by 8 ml square, 2 into E12, E12 or E2. E12 it will become 10 h square by 8 electrons. So this is the energy, third state, the energy of the third state. So we have 2 electrons here. So we'll just double it, 16 h square by 8 ml square, and you just simplify it, it will become 30 h square by 8 ml square. As the answer is given h bar square units, so we know that the duration h bar is equal to h by 2 pi, and h is equal to h square by 4 pi square. Now after h square, we will write h square into 4 pi square. When you simplify, we will get this uh, answer, 30 into pi square h square by 2 ml square. We have 4 here, we have 8 here. For ones are, for twos are, that 2 is this pi square h bar square by 2 ml square, 30 into. So this is the answer for this question. And in this question, a system of 8 non-interacting electrons are there, each of spin 3 by 2 non-interacting quantum particles. These are not the electrons, these are the quantum particles whose spin is given as 3 by 2 in one-dimensional box of length. The minimum excitation energy of the system in the units of pi square h bar square 2 ml square. As we have the number of electrons present in the system is 8 quantum particles are there, 8 quantum particles, each particle having the spin 3 by 2. As the spin is 3 by 2, spin multiplicity is 4. So in each energy level, you can place 4 particles. So in the first energy level, we can place 4 particles, and in the next energy level, we can place 4 particles, and in the next level also we can place 4 particles. As we have only 8, now 4 here, 4 here, we are done. Now we need to calculate the minimum excitation energy, how much energy is required for going E2 to E3. Is for that we need to find the energy of E1 state, and energy corresponds to E3 state, energy corresponds to E2 state. Then take the difference for E3, as it is a one-dimensional 1D box, E3 minus E2 will be 9h square by 8 ml square minus 4h square by 8 ml square, n square h square by 8 ml square. Here n is equal to 3, n square h square by 8 ml square. Here n is equal to 2 because it's a 1D box. So difference is for h square by 8 ml square. That when it's expressed in only h bar square, you would get this minimum energy required to make this transition. Minimum excitation energy of the system. In this problem, a particle is confined in a box of length as shown here, and the length of the box is 0 to L, and this is the point at which L is equal to L by 2. If the potential V naught is treated as a perturbation, if this is the perturbation magnitude of the perturbation V naught, including the first order correction, the ground state energy is. Now we need to first calculate the perturbation energy correction due to this perturbation potential V naught. Then we need to add the ground state energy plus perturbation energy due to the extra energy due to perturbation. That will become equal to the energy of the state. For this, first we should find the first order correction, including the first order correction. The first order correction to the ground state can be written as E11. The first order correction corresponds to ground state. corresponds to, is E11 is equal to, this is the ground state psi1 star, this is the perturbation potential, this psi is again the ground state psi1, we should write psi1 actually here, then psi1 star psi1, this value will become equal to 0 because we will take the normalized wave function, and now this is taken to integration form as this perturbation potential is only from 0 to L by 2. So we need to integrate, the integration limits must be 0 to L by 2 because the perturbation potential would exist till 0 to L by 2, 0 to L by 2. So psi1 star, as psi1 doesn't involve any of the conjugate, any of the imaginary terms. So psi star is same as psi root 2 by L sin pi x. We have this is the perturbation potential. This is the perturbation potential root 2 by L sin pi x dx. Then root 2 by L will become 2 by L and would come outside of the integration. Then sin pi x by L v naught sin pi x by L. V naught also is a constant. It would come outside. So we have sin square pi x by L. So this could be again written into 1 minus cos 2 theta. So 2 v naught by L integration of 2 sin square and pi x by L dx. So we can send this 2 inside. That would become 2. It would look like then 2 sin square theta. That 2 sin square theta can be written as 1 minus cos 2 theta like we did in earlier cases. So we are here now left with v naught by L. This 2 is gone inside and made it 2 sin square and pi x by L. That is written as 1 minus cos 2 pi x by L. So and then you just integrate separately the terms this and this separately. We will get this. This is the integration of cos 2 pi x is sin 2 pi x by 2 pi by L, then that can be taken to the numerator, it will become L by pi. And substitute the values integration limits 0 to L by 8. Here it will be the integration of dx, ax. Integration of dx is 1 between the limits 0 to L by 2. Then v naught by L. So here after the integration limits are substituted, it will become equal to L by 2 minus. So after integration limits are substituted here, it will be sine 2 pi. When x becomes L by 2, it will be sine 2 pi. Sine 2 pi is 0. When x becomes 0, sine 0. The value of this after the substituting the integration limits upper and lower integration will become 0 minus 0. So whole thing will become 0. This would now become equal to v naught by 2. So this is the first order correction to the ground state. First order correction to the ground state. Now the total ground state energy is equal to the actual ground state energy and the energy part from the perturbation E1 n square h square by 2 ml square 8 ml square or it is written in h bar term n square h bar square by 2 ml square. Now this n square will become the value of 1 h square by 2 ml square plus v naught by 2. This v naught by 2 is the perturbation E11. You should write 1 here. The total energy of this system will be ground energy of the ground state energy without perturbation plus the energy contribution from the perturbation. Now, in this case, the particle of mass m is confined to two-dimensional square level potential. The potential is given, and this is the potential constraint. The energy of the first excited state for this particle is the energy of the first excited state. As it is a two-dimensional box, the energy expression is Anx Ny is equal to nx square plus ny square h square by 8m a square. So the first excited state can be described by the quantum numbers 1 and 2 or 2, 1 because in both the directions x and y direction we have the same length. There is no length difference. So these two will give the same answer. So 1 square plus 2 square make it 5h square by 8ml square. And you convert this into h bar units, it will become 5 pi square h bar square by 2ma square. And this problem may be a little difficult. We'll see. The normalized eigenstates of a particle in one-dimensional potential well are given by this is the potential function where it's like this. Potential is equal to 0 in the range of the box length and its infinity. Otherwise, are given by is a wave function corresponding to the 1D bags, one-dimensional bags, a particle in a one-dimensional bags. This particle having the wave function like this, general wave function is given here. It is perturbed using this perturbation potential. Here we calculate the energy using the perturbation potential V naught. Here the perturbation potential is little complex. The perturbation potential is V naught into cos pi x by a in this range of the length of the box, or otherwise it is 0. Otherwise, the shift in the ground state energy due to the perturbation in the first order correction. The shift in the ground state energy. Now we need to calculate the perturbation energy correction to the ground state energy level. So E11, you need to calculate E11, that gives the first order correction to the ground state energy level. To find E11, we need to now having psi 1. Psi 1 is equal to, just place n is equal to 1, that will become psi 1 root 2 by a sine n by x by a. The perturbation potential is, this is the perturbation potential, V naught cos pi x by a. Then we need to construct the equation of the first order energy correction to the ground state E11. That would become equal to psi 1 star. This is the potential potential psi 1 and psi 1 star psi 1. This value will become equal to 0 because we have taken the normalized wave function. Then this is when this is taken to the integration form. This psi 1 star is root 2 by a sin pi x by a V naught cos pi x. This is the perturbation potential. Then psi star and psi both are same in this case because it doesn't involve any complex terms. So root 2 by a are imaginary terms. Then root 2 by a sin pi x. Then root 2 by a will come outside of the integration. Then this bracket form is taken to the integration form. 2 by a, this V naught also will come outside, and we are now left with sin square pi x, sin pi x into sin pi x, sin square pi x by a, and this cos pi x dx. Now this could be solved by substitution method, as it appears in the form of f of x power n times f dash x dx can be solved by the substitution form. We'll make t substitution, t is equal to sin pi x by a, and dt will differentiate this, will become cos pi x by a pi by a. Then at x is equal to 0, t becomes sin 0 0, and at x is equal to a by 2, at x is equal to a by 2. Now we are left with sin pi by 2, t is equal to 1. Now we will make the substitution, x in terms of t, and limits also will be changed. 0 to a by 2 has become 0 to 1. This has become t square dt. Now integration of t square is t cube by 3. That would become, if you apply the limits, that would become equal to, after simplification, then it will become 2 v naught by 3 pi. This is the shift in the ground state energy after the perturbation. This is same as E11, or energy correction to the ground state wave function with this much as the perturbation potential. That's all is about this. If you have any doubt, please write to us for your any of the doubts to this mail ID. We will try to clarify.